Start. The first speaker is T.Nosaka from CISA, and he will tell us about M2-branes and discrete Painleve systems. Please.
Thank you. Thank you for the introduction. My name is T.Nosaka, now postdoc in CISA. So first of all, I'd like to thank the organizers for giving me a chance to speak. Today I'm going to talk about my latest work, which is on the partial function of the theory of M2-branes on 3 sphere and its relation to the nonlinear differential systems, such as the Painleve equations. Let me start with the introduction. The efficient theory is the maximal or almost maximal supersymmetric 3D supermodern Chern-Simons theory in 3D. Sorry, I said 3D twice. And it's the theory of n-stack M2-branes on this kind of orbifold. Therefore, this efficient theory is one of the most fundamental examples of the ADS-FT correspondence in the same sense that the 4D maximal supersymmetric image theory, which is theory of the stack of the brane, is. And in the current case, the efficient theory is due to this gravity space-time ADS4 class system over ZK. And thanks to the supersymmetry, we can calculate the partial function of this theory on 3 sphere, which is originally defined by the path integral as an n-dimensional ordinary integration, which in this talk I'm going to call as the matrix model. And furthermore, there are many techniques with which we can further evaluate that matrix model around the Radian limit. And actually, thanks to the many efforts, now the efficient matrix model was completely solved in the sense that now we know all of the one-on-one corrections. Here, I'd like to briefly summarize the results since it's also relevant to what I'm going to say later. First of all, the free energy, the log partial function of the efficient theory starts from the M2-3 halves. The scaling is the famous M2-3 scaling of the M2-brane entropy, and we can reproduce this from the matrix model. And furthermore, now we know the order 101 particle correction, and it was found that these order corrections add up to the single function, the early function. And there also exists the 101 non-particle correction, which looks like this. And again, we have infinitely many corrections. We have a series of this exponential minus square root k, exponential minus 2 square root k, and so on. And we also have this sequence. So you have infinitely many non-particle correction, but again, this image series can be reproduced by the quantity called the free energy of the defined Folksky string free energy. Sorry, I said free energy twice. Anyway, so now we know everything is a 3. And actually, part of these results are also reproduced from the other side. For example, this leading part is reproduced by the classical action of the 11-dimensional supergravity. And also this log correction is reproduced by the one loop effect. And also these non-particle effects, this exponent of the non-particle effect, actually in the current setup, the ADS4 radius is proportional to M2-1/6. So this implies that there is some 3-dimensional object. And the gravity interpretation for these two things are actually the closed M2-brane propagating on the bulk, which is different from what I'm considering here. And wrapping on some non-trivial 3 cyclone DS7 over ZK. Since such M2-branes from the viewpoint of ADS4 is localized both in the space direction and time direction, we sometimes call this effect of the instanton, M2 instantons. And there are two kinds of the winding. One is the 3-dimensional direction, which doesn't involve the ZK orbifold, and the other involves the ZK orbifold. So there are two kinds of the instant effect, which is completely in agreement with what we found in the field theory side. So some of these exact results are known from the gravity side, but almost all of the exact results are still unknown from the gravity side. That means that these exact results are giving non-trivial prediction to how to incorporate how to formulate the quantum effect of the gravity. For example, there is an argument that this order non-perturbative correction, sum up to the Airy function, may be reproduced if I apply the same idea as the supersymmetry localization technique to the supergravity. It's proposed by these people. So we know the Lagrangian expansion of the efficient partition function, and once we know, once we solve exactly the simplest case, it's very natural to ask about generalization. And we can consider many kinds of generalization. For example, we can consider this rank deformation. The original EVGM theory is defined by two gauge group. And in this case, I said this rank of the two gauge group equal, but we can take it different. And also, the EVGM theory can be interpreted as the circular quiver with two nodes, but we can also consider the circular quiver with more than two nodes, or even non-circular quivers. And we can consider such thing, but what I'm interested in these days is not this, but rather the EVGM theory with mass deformation, mass parameter added to the mathematical rate. This deformation is, first of all, it's useful since if we calculate the partition function, take the derivative by mass and take mass to 0, we can consider something other than the partition function, which is expectation value of the currents coupling to the mass deformation. Maybe the fact that we can calculate such thing itself is interesting, but besides that, these quantities also play a nice role as an input parameter in the superconformal bootstrap, which have been worked out recently by these people. But the reason why I'm interested in this mass deformation is something different. Actually, one might think that this deformation is somehow trivial, but actually this is quite non-trivial. Because when mass is very small, actually everything that we obtain is a very simple generalization of the EVGM results. But what we found in the previous work is that when mass reaches some critical value, we encounter the Lagrangian phase transition. And there's an interesting interpretation of this phase transition in the gravity side as something which may call the condensation of the M2-brane instances, which I'm going to explain later. So these are the reasons why I'm interested in this model. But unfortunately, this Lagrangian phase transition happens at the same time that the non-Lagrangian techniques stop to work. So we cannot study the phase transition itself and the supercritical regime by the non-Lagrangian techniques like the Lagrangian solver approximation or the formalism. So what I think I think before doing this my recent work is if studying the Lagrangian limit is difficult, how about studying the finite end property of the partition function? But what we want to get is some finite end property, but which is valid for any mass parameter. And since the phase transition happens only in the Lagrangian limit, as long as the number degree of freedom is finite, there are no phase transition. So if n is finite, even we take the mass larger than the critical value, everything is smooth. So I expect that if there are some nice relation for finite n, it's valid for any value of the mass. So maybe from that structure, maybe we can extract some hints to understand the phase transition also. That's what I hoped. And actually, it's known that the EVGM matrix model of the theory and its generalization of the particular structure which allow the matrix model which allow us to relate matrix model to the nonlinear system like Painlevé or Toda equations. And actually, by using this structure, I identify the corresponding nonlinear system for the partial function of massive efficient theory, which is a kind of generalization of the QD-formed Toda equation. So this is from my talk. So I already finished introduction. And now, after that, now I'm going to introduce the massive efficient theory and display the matrix model expression for the partial function. And then I review the evidences for that this theory, the partial function exhibits the large n-phase range at some finite mass parameter. And after that, I move to the finite and property of the partial function. And then I summarize my talk and show several candidates to choose the works. So let me start. First of all, the efficient theory consists of, in the language of 3D supersymmetry, consists of the n equal to vector multiplied with Chern-Simon action. And we have two such vector multiplied with Rebecca and minus k, and the Chern-Simon action looks like this. And we also have the 4 by fundamental chiral multiplied. And we have the SE4R symmetry, which makes this 4 by fundamental chiral multiplied. And to introduce the mass deformation, what we have to do is to turn on the background vector multiplied for the U1 subgroup of this R symmetry, and give some wave of that vector multiplied, which preserves the supersymmetry. And what I'm going to do in this talk is to choose this U1 subgroup as the U1 of the SE2 cross SE2 of the SE4, and give the mass parameter to each U1. In the Quiver diagram, what this means is that originally we got 4 by fundamental chiral multiplied completely on equal footing, but I split it to 2 and 2 and giving different mass parameters. And to this, the partial function of this theory, we can apply the technique so-called supersymmetry localization formula. And the general formula looks like this. Originally, the partial function is defined by the path integral, but if we have this supersymmetry, it leads to the sum over only the supersymmetry invariant configuration, not the configuration, functional configuration, or origin functional configuration. And what we have to sum over such configuration is just the classical action evaluated by that configuration and the one perfect. And this is the result for the mass geometry efficient theory. I'm not going to explain, but I'm not going to explain derivation, but instead I'm going to explain the interpretation of each component. First of all, this integration corresponds to the sum over the supersymmetric configuration. In the current case, it's given by the sigma equal d equal constant, and the constant can be anything, so yeah, I have to integrate. And this part comes from the classical action, from this part, and this from the one predeterminant. And the first evidence for space transition was found by evaluating this partial function by the saddle point approximation like this. So if I put everything in the integrand in the exponent, I can evaluate this n-dimensional integration by the saddle point approximation, which approximates this n integration by the contribution from the saddle. We will solve these equations. And these equations are very complicated, but if we consider the case with equal masses, actually we find a nice answer to solve this equation in the large n limit, which looks like this. Here S corresponds to the index of the eigenvalues. So we originally have the n discrete eigenvalues, but in the large n limit, it looks like the continuous distribution. And actually, to solve this other equation, we also have to assume this. This is needed to expand the symbolic functions around the large eigenvalues. This is just technical assumption. But anyway, if we assume these two, I can solve this other equation. And for Z1, Z2, and substituting it to the effective action, I get to this free energy N2 have scaling free energy. But what we found in this previous work at the same time is that when mass is small, this analysis is valid, but when mass is greater than or equal to pi, the analysis becomes inconsistent. The way the inconsistency comes is, so it's very technical, but is the following. If actually the Z2 looks like this, I'm plotting the trajectory of Z2 as I vary S from -half to half. It looks like this. And when mass is 0, it's just straight line connecting from here and here. But as I increase mass, this becomes larger and larger in this direction. And actually, when mass approaches the pi, this explodes. It goes to infinity. So it's problematic. Still, one might ask that maybe we can formally quote the solution for small mass and just substitute to mass larger than pi. Then it looks like this. This itself is not so problematic, but actually, if I plot this function, we found that it exceeds the bound. Actually, it goes to infinity. So in that sense, there is an inconsistency if we try to solve the equation for mass larger than pi. We made several efforts to find the alternative solution analytically and also numerically, but we couldn't find, unfortunately. So anyway, this inconsistency suggests that we have a phase solution at n equal to pi. And I also have other two evidences, but to explain them, I have to introduce the Fermi formalism for the partition function. It's like this. We can rewrite this partition function in this way. And actually, we can further rewrite this in this way. Actually, if you know the formula, this looks like the Cauchy determinant formula. So this and this together is the determinant. And actually, we can further write it as by introducing one-dimensional quantum mechanical notation and regards that the matrix element of determinant as the quantum mechanical matrix element with the position eigenstate lambda. And it looks like this. Actually, the writing is very useful because we can evaluate the partition function systematically in the small k limit. Actually, to study partition function, it's more useful to study the ground potential defined by this instead of directly studying partition function. But actually, they are equivalent. Once we know the ground potential, we can reproduce the original partition function by this inversion formula. And actually, this ground potential looks like this. So we can expand this in the power of exponential mu, and it looks like this. And what we have to evaluate the ground potential is to evaluate this trace of the quantum mechanical operator. But there is a very nice formula to do the semiclassical expansion of the trace of the quantum mechanical operator, which is called the Wigner transformation. And it looks like this. And the Wigner transformation. So the method tells that if we know the Wigner transformation of the operator, we can evaluate trace by integrating that Wigner transformation, which is function in phase space over the phase space divided by 2 pi h bar. And this Wigner transformation itself have the h bar expansion like this. The most leading part is L equals 0 is simply this row with x and p replaced by just c over x and p. And by using this expansion, I can rewrite the ground potential like this. And actually, at each order in the h bar expansion, we can explicitly perform this integration for arbitrary n. So we know the general expression for n, arbitrary n. So we can resum this sum over n. And in particular, if we do the large M expansion of the each order of the small h bar expansion after the summation, we obtain this series expansion. The first part, the cubic term in mu, have only the 1 over h bar order. And the second term have only the 1 over h bar and the order h bar. And this A actually have the all order correction, but actually we can easily guess the expression of this A from the non-expression of the division without mass deformation like this. And we also have these two, which this part also have the all order correction in h bar, and we don't know what it is. And also this, we in principle also have this, but we cannot study this at all in the h bar expansion since we have 1 over k here. However, if we are interested only in the 1 over part of the correction of the partial function, we don't need these two, because as I said, once we know the ground potential, we can get partial function by this inversion formula. So, and if we are interested in large n, what we should do is to consider the saddle to evaluate this mu integration as the saddle approximation. And if I plug this into here, we find that the third point value of the mu is like square root of n. So actually these two contributions are non-perturbatively suppressed in the large n limit. So, and from these three parts, we get the R function. So very simply, we can get the all order 1 over n correction just by studying first two order of the symmetrical expansion. It's very nice. And we can also check that this is indeed a good approximation, since we can also calculate the partial function for finite n and compare. We can compare it with this area function, and we find very excellent argument like this. And one thing which is very important is that this area function is completely regular. It's completely smooth, even if the mass parameter crosses pi. So from this analysis, one may think that there are no phase transition. But however, if we compare the exact value and the area function for mass larger than pi, I found the discrepancy. So this suggests that there is actually phase transition. And also, if we study the mass dependence for each fixed n, we find that the partial function behave completely different way between mass less than pi and mass greater than pi. For mass less than pi, it's quite smooth, but as mass becomes larger than pi, it starts to oscillate very rapidly, and actually partial function even becomes 0 at some value of the mass, and it becomes negative and oscillate. So this result, the finite n result, actually suggests that there is indeed a phase transition, and the phase, subcritical phase and supercritical phase are quite different. So there must be some problem in this perturbative analysis, and that must be, so there must be something wrong in the non-perturbative effect. So let me review about the non-perturbative effect. As I said in the introduction, there are two kinds of the non-perturbative effect in the evidence theory, which looks like exponential minus square root of k and exponential minus square root n over k. And if I translate it to the ground potential, it looks like exponential minus mu and exponential minus mu over k. So also in the mass deformed diffusion case, it's very natural to expect that we have this kind of instance with the coefficient depends on the mass parameter. And actually, this one can be studied by the semi-classical expansion. Also, we don't know how to resum the overall coefficient, but if we just want to know the instant exponent, it's enough to study only the first few terms in the small h by expansion, and we found this kind of instant. And nicely, this, as long as mass is real, the real part of the instant exponent are always negative. So they are indeed exponentially suppressed in the large M expansion, or equivalently in the large N expansion. And next, let's look at this instant effect. Since we have 1 over k here, we cannot study it in the h bar expansion, but we can study in the following way. So since we can calculate exactly the Flash function, we can calculate the deviation between that exact value and the part of the part. Again, we obtain the exact deviation. And now supports the ground potential of this non-perturbative correction. Then from this inversion formula, this is translated to this relation. So this means that if I plot the z over z part -1 and plot it in log with horizontal axis this, we can read off the instant exponent by fitting this by the straight line. Actually, what I should do is not fitting, but just take only the largest two values n and connect it by the straight line, because this expansion becomes better and better as n increases. Anyway, by doing it for various values of the mass parameter and the Chern level, I obtained this. And actually, this is problematic because when mass parameters are small, the real parts of the instant exponent is small, but as mass parameter reach this value, square root of M1, M2 become pi square. The real part becomes 0, and after that, the real part become positive. So that means that when mass is larger than that value, these effects are not exponentially small anymore, but exponentially large. So this means that when mass is larger than the critical value, the perturbative, the part is not correct, not the correct expansion point in the large N limit. So I provided the two other evidences before, but they are not so convincing. But I think this is really proving that there is a phase transition. By the way, in the Evgem case, this non-perturbative edge are interpreted as the closed M2-branes bulk winding on the S7 over ZK. So this phase transition caused by the divergence of the non-perturbative edge suggests that the phase transition corresponds in the gravity dual side to a new phenomena that the M2 instantons start to condensate, M2 instance condensation. So I finished reviewing the evidence for the Gaussian phase transition of the massive dimension theory. So now let me move on to the finite time property. So let me summarize what I said so far. So I provide several evidences, and now I think it's convincing enough that the massive dimension theory actually exhibits the large N phase transition at m equals pi. And it sounds interesting, like the gravity dual interpretation of the instant condensation. But actually, since the phase transition are predicted as the breakdown of the large analysis, we cannot study, although we can predict the existence of the phase transition, we cannot study the phase transition itself and the supercritical regime by the known large N techniques. So that's the trouble. And what I thought is maybe if some finite time property of the first function may be helpful. And actually, it's known that it's known in many contexts that there are relations between some kind of matrix model and nonlinear differential systems. And what I used in my research is in particular something generated by this complicated diagram. I'm going to briefly review each part later. And actually the relation we obtain this way involves matrix model also finite. And so now let me briefly sketch what each component of this diagram means. First of all, let me talk about the Painlevé equation. Historically, there are some interest that since we can use the linear ordinary second order linear ordinary differential equation to define the special functions. For example, we can define the hypergeometric differential equation, define the hypergeometric function. Then people are interested in how about the nonlinear second order differential equation to define some new kind of special function. It may be interesting, but since nonlinear differential equations are quite a huge group, maybe we should import some special property. And what was thought in the old days is something called the Painlevé property, which means that the solution of the differential equation shouldn't have the branch point which depends on the initial condition. It's okay to have the branch point which depends on the equation itself, but we shouldn't get something like that depending on the initial condition. For example, this is not second order, but let's consider the first order differential equation like this. This is in general non-linear, but maybe we can just solve it and we get this. And for example, for alpha equals 0 or 1, this is regular, so it's okay. But for alpha equals 2, we have the pole, but pole is still okay. But for the other values alpha, we get the branch point at t equals t0. T0 is the initial condition, so it's not allowed. Painlevé equation is something like that. And the nonlinear, the second order ordinary differential equations with this Painlevé property were classified by Painlevé as these, except those trivial ones. And I'm not going to use this explicit expression, but let me just show something. The leftmost one looks like this. And it have the four pre-parameters. And this the second order nonlinear differential equation for lambda with the variables t. And actually, all the other Painlevé equations obtained by taking certain limit from this. Certain limit means you have to take this theta to 0 infinity, but that's not enough. We also have to send scale t and lambda and send to 0 infinity. But anyway, all the others are obtained by some kind of reduction. And the rightmost one, which is called the Painlevé tree, looks like this. And let me note that actually this Painlevé tree is equivalent to something called the affine SF to Toda. That means closed Toda chains with two particles, which looks like this. We have two particles, but since the center of mass zero and decoupled, what we have actually is the second order nonlinear differential equation for single variables q1 minus q2. And I'm not going to show, but by some very non-trivial rewriting, we can rewrite it in this way. I told you these facts because this Painlevé tree is the relevant case to the mass differential region theory, and actually this SU2 picture is the crucial. And let me move on to this part. So to do this part, so what we want to do is to relate Painlevé to some 2D safety. And it can be done in this way. Actually, the Painlevé nonlinear Painlevé equation can be formulated in equivalent way, but linearly by considering something called the isomorphic deformation problem. on punctured sphere. That's like the following. Let's consider this linear differential equation with two component vector psi, and each A are 2 by 2 matrix satisfying this property. And we can solve this equation locally around z equal to Ti, and we found something like this. This alpha is just A. This means that for generic matrix A, generic variability matrix element A, we have the non-trivial monodromy as I move Z around Ti. And what the isomorphic deformation problem means is that we vary Ta and at the same time also vary Ai covariantly, so that this monodromy property is preserved. And from this expression, we find that to preserve the monotony, we have to the T derivative psi should be like this. It should something looks like the Z derivative around Z equal to Ti. So it should be looks like this. And from these two equations, we can consider consistency condition, that is commutativity of the Z derivative Ti derivative. And we get to this. So we started from the linear equation, but we eventually get the non-linear equation. And in particular, if we consider the case with 4 punctures, then we can rewrite this to the Painlevé non-linear equation. Actually, there are many conserved quantities of this system. And this conserved quantity, actually, they are the eigenvalues of the A, matrix A, identified with the parameter, free parameter of the Painlevé. And the remaining non-conserving component of the matrix is identified as the lambda T. And so in this way, the Painlevé system, we can associate the Riemann surface to the Painlevé system. And furthermore, I'm not going to explain detail, but if we define the type function, isomorphic type function in this way from A, that means from the lambda also, then this tau is given by the safety quantity, the 4-point function, since we are considering 4 punctures, of the review safety with temperature 1. I'm not going to explain why this is the case, but I'm going to put a fact which might be helpful to convince you that this is indeed the case. That is the following. Let's consider the case with 3 punctures, not 4 punctures. Then actually this sum AI equal to 0 is too strong that we find that all the stress AI edge are conserved. So we can just integrate this equation and we get this. And you know, this have the completely same T dependence as the safety 3-point function. So since we have the safety 3-point function for 3 punctures, maybe it's not so unnatural to guess that the 4-point function case, 4 puncture case is corresponding to the 4-point function. I'm not going to explain anymore. So next, let's move on to this part. So I want to relate to this F2 to the 4D mills. It can be done by considering the M5-brane configuration on compact lines on the product manifold of 4D and 2D. That is, if I reduce the theory of M5-brane over this by sigma 2, we get some 4D theory, which is determined by the property of the sigma 2 on M4. And if we do the convection on the other way around, what I get is the 2D theory, which is determined by the 4D manifold on the 2D. And since the two theories originate from the same setup, it's nice to guess the relation between these two. Actually, the concrete relation was studied by Ardaiga Tachikawa, and this is called the 4+2 AGT correspondence. And the 4D theory, which arises for the 4-puncture sphere, is actually the 4D SU2 theory with 4 fundamental matter magistrate. And the HT dictionary tells us that the CFT correlator is given by the first function before the theory on the omega background R4. And for the theory 2 is defined by the definition for the theory of the parameter like gauge coupling, and if we have the mass matter phase, we have the mass parameter, and the first function also have the parameter which correspond to the Coulomb-Webb observational magistrate. And these parameters are corresponding to the theory parameters by the dictionary like this. Gauge coupling correspond to the complex moduli. In our case, just T. Masses correspond to the formal weight of these 4 operators. And the Coulomb-Webb correspond to the formal weight of the internal state. And these quantities are further corresponding to the Painlevé parameters like this. And there are no parameter. Actually, there are no parameter corresponding to the Coulomb-Webb in the Painlevé equation motion, but since that's the differential equation, we have to specify the initial condition to specify the solution, and the Coulomb-Webb corresponds to the initial condition. And now I explained only the Painlevé 6 case, but as I said, the other Painlevé is obtained by some kind of the reduction. And in particular, this sequence, the reduction of this sequence precisely corresponds to the massive coupling limit of the 4 matter SU2M theory like this. And the relevant example to the massive modulation theory is the last one, which is the relation between the Painlevé territory or affine SU2 Toda, and the counterpart. For the counterpart is the PML theory. And then next, I'm going to this part, briefly sketch that part, and to relate to the structural problem and 5D theory, we should consider the algebraic curve looks like this. And once we are given this curve, we can do 2 things. First, we can quantize it. What I mean is that introduce the quantum mechanical operator and replace the coordinate of the curve like this, and impose x and p commutation relation like this. And then the O defining the curve become the quantum mechanical operator. So we can consider the eigenvalue problem like this. And in this problem, which is called the quantum curve, the natural quantity we can consider is something called the spectral determinant. Looks like this. This encodes all the information of the eigenvalues like this. This is equal to this. And the other thing we can do is to draw this curve and to extract the skeleton of this curve and regard it as the PQ5 brane web consisting of the NS5 brane and D5 brane and the bound states. And then once we are given such PQ5 brane web, there's a way to associate the 5D n equal 1 theory to that wave diagram. So from this curve, we obtain the two pictures, the quantum spectral problem and the 5D n equal 1 theory. And actually, it's known that the 2 theories are related in this way. The spectral determinant is actually equal to the Fourier transformation of the 5D partial function on R4 omega background R4 times S1. And again, the 5D theory have the theorem parameter of the theory, GM is coupling, and if we have the matter field, the mass parameter. These parameter of theories are encoded in the coefficient of the curve. And to define the partial function, we also have to specify the Coulomb-Webb, and this corresponds to this copper spectral parameter here. And actually, I just gave a hand-waving argument why we have this relation. I didn't explain at all. And actually, I think, as far as I know, there are still no rigorous proof for this relation for complete general setup. But what is important is we can check this relation explicitly. What I mean is that the probability partial function is given by the instant exponent. So if we truncate the instant sum at some finite order and also truncate the sum of n, we can evaluate the right-hand side quantitatively. And in particular, we can find the zero as a function of sigma, at least numerically. On the other hand, we can calculate the eigenvalues of this quantum operator by whatever. For example, we can expand this psi by the harmonic oscillator eigenvalues and truncate this infinite complete set at some order.
5 minutes.
Thank you. I'm almost finishing. And so we can determine the eigenvalues numerically, and we can also determine the zero with the right-hand side, and we can check that they indeed agrees with each other. And so if I assume this and combine this result with the Painlevé gauge correspondence, which I showed in the previous slide, we finally get this relation. And as I said a bit, since we are considering 5D theory, not 4D theory, the relation is slightly modified, and we get to give it instead to the shifty, and we get the Q difference equation instead of the differential equation, which means that the T derivative is replaced in this way. Anyway, we get the relation between spectral determinant and the type function of the difference system. And we can expand the spectral determinant in this way. So actually, spectral determinant is generating function of the matrix model. So in this way, we got the relation between matrix model and the type function of the nonlinear difference system. And now we apply this to the massive dimension theory. As I told in the beginning, by applying Fermi formalism, we can rewrite the partial function in this way. So we are almost ready to apply the idea what I told in the previous slide. If we define the ground partial function in this way, this corresponds to the spectral determinant. But the problem is that when mass is a generic real number, this is not we cannot expand this in an integer power with these T star operators. So let us first assume that the masses are given by minus pi I times some rational number, which I'm going to write in this way with mu and a integer satisfying this. Then we can take the long inverse trivially, and we get this. And now all the powers are integer. So we can do the argument in the previous slide. And to obtain the 5D theory for peak wave diagram, it's convenient to consider the Newton polygon of this equation. That is the points on the ML plane which exist in the right-hand side. For example, in the case nu equal 4 and a equal 1, we get this. And this is important because the peak wave diagram is immediately obtained by taking the dual diagram of this. In this case, it's like this. And this corresponds to the 5D SU nu EM theory with no matter field because the rule to read of the 5D theory from peak wave is that if we have the horizontal line extending to the infinity, it corresponds to the matter field, but since there are none of them in this case, we don't have the matter field. And the number of horizontal plane in internal horizontal plane corresponds to rank. So we get this. And I didn't tell what is the corresponding the nonlinear system, but since the 4D SU2 corresponds to the Painlevé tree, which is equivalent to the SU2 toda, affine SU2 toda, it's very natural to guess that 4D SU nu will be corresponding to affine SU nu toda, and maybe 5D corresponds to the Q deformation. So we can guess. And whose equation motion rate in tau form is like this. So we are almost done, but since this is the evolution equation for t, we also have to turn on the time t. And as I said, this is encoded in the quotient. And actually, we can turn on the quotient by turning on the rank difference like this. And what we finally get is this. Again, the arguments are hand waving, and I didn't explain at all about such coefficient, but the important thing is we can check this. Since this, if we expand this equation by a small couple expansion, what we get is infinitely many binary equation for the partial function finite n. And since we can calculate the exact value of the partial function, we can check it order by order. And I did it, and I found this is indeed the case. So this isn't my talk. So let me summarize. So I'm interested in the maximum division theory because it expresses quite non-trivial phase transition at finite mass planeta and finite k, which in the technical terminology called the M0 region. And this phase transition may have the gravity interpretation of the condensation of the M2 instanton. And also from the finite n exact value, we found that the subcritical regime and supercritical regime are completely different quantitatively. Sorry, qualitatively, even qualitatively. So I think this phase transition is interesting, but unfortunately, we cannot study the phase transition by the non-Largen technique. So what I thought maybe finite property is helpful. And with this motivation in my mind, I found relation among the partial function of the mass efficiency, which hold for finite n, which looks like this. And these contain infinitely many relation between the partial function with mass efficiency for finite n. And in the previous slide, I assumed that mass is given by this, but since this equation holds any new array, actually this span the dense set in the imaginary direction. And since partial function for finite n is completely holomorphic in mass, that also implies that the identity holds also for completely general value of mass. In particular, even for the supercritical value of the real mass. I hope this helps to understand the phase transition of the mass efficiency theory. And this is the list of the future work. First of all, in this talk, I consider only the case with equal mass, but it will be nice if we can do the same thing for the non-equal mass. And also, as I said in the introduction, the key point to get nonlinear equation was the Fermi formalism. And it's known that many example theory of the M2-branes allow the rewriting of the partial function in the Fermi formalism. Yeah, actually, those which I showed in the introduction, the circular quiver with many nodes and the non-circular quivers allow the Fermi formalism. So it would be nice if we can find a similar nonlinear relation also for such theory. Or conversely, if we can find the matrix model which corresponds to the nonlinear system, not included in the Painlevé or this SU Newton. And also, since the binary relation holds for arbitrary mass, it also gives the relation for the derivative of the partial function. So maybe it can be used in some way in the context of the bootstrap, where the expression value of the operator calculated by the mass derivative of the partial function plays a nice role. And actually, I said I hope that this binary relation helps us to understand the phase transition. I'm not completely sure because it's evolution equation not in mass, but in the rank difference. So it would be nice if we can find another kind of the exact relation for the partial function, which is the evolution equation for mass rather than rank deformation. And lastly, in this talk, I emphasize again and again that the phase transition is interpreted as M2 instant condensation because actually such phenomena, the condensation of some extending object wrapping on some internal space of the gravity. I think this is ubiquitous. I think same thing can happen also in different setup as long as we have some compact non-trivial direction in the dual gravity. So it would be nice if we can find this similar phase transition in other setups. And what I in particular have in my mind is the supercommon index of the 4D Yamil theory, 4D maximally supersymmetric Yamil theory, which have been studied quite intensively these days. This is the end of my talk. So thank you for your attention.
Thank you. Any question? Okay, so if there are no questions, we can move to the next speaker.